transfer switch doesn't necessarily have to switch the neutral, but it's crucial that it switches the ground. The generator ideally should bond the neutral and the ground, though it isn't strictly mandated to be bonded to the frame itself. The number 10 ground wire that runs from the generator to the transfer switch is typically adequate for grounding the generator. That external ground lug you see in the generator can be used to ground the frame directly to the earth. This doesn't create a parallel ground path because this lug isn't tied to the neutral conductor. The grounding system for a generator is engineered with primary goals of protecting both people and equipment from the dangers of electrical shock. That ground lug on the exterior of the generator serves a critical purpose. It ensures the frame is grounded to the earth. This connection brings the frame to the same electrical potential as the earth itself, greatly diminishing the risk of electrical shock if a fault occurs. The number 10 ground wire connecting the generator to the transfer switch is responsible for grounding the generator to the broader electrical system. This ensures the generator is correctly grounded and that there's a low impedance path for fault current to flow, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses. The purpose of grounding is to provide a safe path for fault current to return to the source. Without a proper ground, fault current could flow through unintended paths, such as a person touching a faulty appliance, which could result in serious injury or death. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that electrical systems are installed and maintained in a safe manner. Understanding the NEC requirements for grounding is essential for anyone working with electrical systems. The NEC Section 250 covers grounding and bonding. Section 250.20 specifies the systems that must be grounded, while Section 250.24 details grounding electrode system requirements. Section 250.50 discusses grounding electrode systems and their connections. Section 250.166 covers sizing the grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the ungrounded conductors. Table 250.66 provides guidance on sizing the grounding electrode conductor for alternating current systems. Bonding ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Section 250.92 covers bonding of metal enclosures. Section 250.96 covers bonding other enclosures. Section 250.102 details bonding jumper requirements. Sizing bonding jumpers is crucial for effective fault current return. Generators are typically installed with an automatic transfer switch or manual transfer switch. The transfer switch allows switching between utility power and generator power. When the utility power fails, the transfer switch starts the generator and transfers the load to the generator. When the utility power is restored, the transfer switch transfers the load back to the utility power and shuts down the generator. Transfer switches are available in various configurations, including non-separately derived systems and separately derived systems. In a non-separately derived system, the neutral conductor is not switched. The neutral conductor remains connected to the utility neutral. In a separately derived system, the neutral conductor is switched. The neutral conductor is disconnected from the utility neutral when the generator is operating. When using a separately derived system, the generator neutral must be bonded to ground. This is typically done at the generator. The bonding location should be clearly identified. The equipment grounding conductor provides a path for fault current to return to the source. The equipment grounding conductor connects non-current carrying metal parts to the grounding system. This helps to ensure that the equipment is properly grounded and that there is a low resistance path for fault current to flow. The equipment grounding conductor is typically a green insulated wire or a bare copper wire. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. Table 250.122 provides guidance on sizing equipment grounding conductors. Grounding electrodes provide a connection to the earth. Common grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode system should be installed in accordance with NEC requirements. The grounding electrode conductor connects the grounding electrode to the grounding system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The generator frame should be grounded. This can be done by connecting a grounding conductor from the generator frame to the grounding electrode system. The grounding conductor should be sized in accordance with NEC requirements. A parallel ground occurs when there are multiple paths for ground current to flow. Parallel grounds can create circulating currents and voltage drops. These circulating currents can cause equipment to malfunction. Parallel grounds can also increase the risk of electrical shock. To avoid parallel grounds, it is important to ensure that there is only one path for ground current to flow. This can be achieved by properly bonding and grounding the electrical system. Grounding and bonding are essential for electrical safety. By properly grounding and bonding the electrical system, one can reduce the risk of electrical shock and equipment damage. Consulting with a qualified electrician is recommended for any grounding or bonding questions. A qualified electrician can ensure that the electrical system is installed and maintained in accordance with NEC requirements. For a 15 kilowatt generator, the size of the grounding conductors and overcurrent protection would need to be calculated based on the specific voltage and amperage ratings of the generator and in accordance with the National Electrical Code. The ground lug on the outside of the generator frame is specifically for connecting the generator frame to earth ground. This connection ensures that the generator frame is at the same potential as the earth, reducing the risk of electric shock should a fault occur within the generator. The number 10 ground wire from the generator to the transfer switch provides the equipment grounding path. This path is necessary for the proper operation of overcurrent devices in the event of a ground fault. The transfer switch plays a crucial role in the grounding system. It must be designed to maintain the integrity of the grounding path when switching between utility power and generator power. The neutral conductor may or may not be switched, depending on whether the system is separately derived or not. If the neutral is switched, the generator must be bonded to ground. If the neutral is not switched, the existing grounding system can be used. Grounding is not just about safety. It also helps to reduce electrical noise and improve the performance of sensitive electronic equipment. A properly grounded system can minimize the risk of voltage surges and other electrical disturbances. The National Electrical Code is updated every 3 years. It is important to stay up to date on the latest code requirements. The NEC provides detailed information on grounding and bonding. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections can corrode over time, reducing their effectiveness. The grounding electrode should be checked periodically to ensure that it is still making good contact with the earth. The resistance of the grounding system should be measured periodically to ensure that it is within acceptable limits. A high resistance grounding system can indicate a problem with the grounding connections. When working with electrical systems, always follow safe work practices. To energize the circuit before working on it, wear appropriate personal protective equipment. Use properly insulated tools. If unsure about any aspect of electrical work, consult with a qualified electrician. Electrical safety is a serious matter. Taking the necessary precautions can help to prevent accidents and injuries. The generator specifications, including its voltage and current ratings, determine the appropriate size for the grounding conductors, referencing NEC tables such as 250.66 and 250.122 for proper sizing based on the generator's output. The ground lug on the generator frame connects to a grounding electrode system, typically consisting of ground rods or other approved electrodes, ensuring a direct path to earth for fault currents. This connection minimizes the risk of electrical shock by maintaining the frame at earth potential. The number 10 wire running from the generator to the transfer switch functions as an equipment grounding conductor, providing a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protection devices like breakers or fuses. The transfer switch is integral to the grounding system. It maintains the integrity of the grounding path during power source switching, preventing hazardous voltage buildup and ensuring continuous grounding protection. Whether the neutral conductor is switched depends on the system configuration. In separately derived systems, the neutral is switched and must be bonded at the generator. In non-separately derived systems, the neutral remains connected to the utility, and the generator grounding relies on the existing system. Effective grounding not only protects against electric shock but also mitigates electrical noise, enhancing the performance of sensitive electronics. A robust grounding system minimizes voltage surges and other electrical disturbances, ensuring stable and reliable operation. Staying updated with the NEC is crucial, as it's revised every 3 years. Consulting the latest edition ensures compliance with current safety standards and best practices for grounding and bonding. Regular inspections and maintenance of the grounding system are essential. Corrosion can compromise connections, reducing effectiveness. Periodically check grounding electrodes for secure earth contact and measure system resistance to identify potential issues. High resistance indicates connection problems needing immediate attention. Always adhere to safe work practices when dealing with electrical systems. De-energize circuits before working on them, wear appropriate personal protective equipment, and use insulated tools. When in doubt, seek guidance from a qualified electrician to ensure safety and compliance. When you refer to the number 10 ground wire, you mean an American wire gauge, or ALC, number 10 copper wire. Different metal types and insulation types can change the current carrying capacity of the wire. The number 10 AWG wire has a diameter of roughly 0.1019 inches. You can use a wire gauge tool to find the size of the wire. The ground logo on the generator allows for the generator's frame to be connected to a grounding electrode. Firstly, this ensures that the generator frame is at earth potential and helps minimize the risk of electric shock. Secondly, it helps provide a path for fault current to flow back to the source in the event of a fault. This helps ensure the rapid operation of overcurrent protective devices such as circuit breakers. Thirdly, it can also help reduce electrical noise and improve the performance of sensitive electronic equipment. The ground lug on the generator should be connected to a grounding electrode system that meets the requirements of the NEC. This may include ground rods, ground plates, or other approved grounding electrodes. The grounding electrode system should be installed in accordance with the NEC. The number 10 wire that connects the generator to the transfer switch serves as an equipment grounding conductor. Firstly, this conductor is responsible for providing a low impedance path for fault current to flow back to the source. Secondly, it helps ensure that non-current carrying metal parts of the generator and connected equipment are at earth potential. Thirdly, the equipment grounding conductor is sized based on the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. The transfer switch plays a critical role in the grounding system. Firstly, it must maintain the continuity of the grounding path when switching between utility power and generator power. Secondly, depending on the type of transfer switch, the neutral conductor may or may not be switched. Thirdly, if the neutral is switched, the generator must be bonded to ground, typically at the generator. The NEC defines a separately derived system as an electrical system where the neutral is switched at the transfer switch. Firstly, in this type of system, the generator is considered a new source of power, and the neutral must be bonded to ground at the generator. Secondly, this bonding provides a low impedance path for fault current to flow back to the generator, which is required for proper operation of overcurrent protective devices. Thirdly, the bonding location must be clearly identified, and the bonding conductor must be sized in accordance with NEC requirements. The NEC also defines a non-separately derived system. Firstly, in this type of system, the neutral is not switched at the transfer switch. Secondly, the generator relies on the existing grounding system provided by the utility. Thirdly, in this case, the generator does not need to be bonded to ground, as the neutral is already bonded at the service entrance. When designing a grounding system for a generator, it's important to consider the following factors. Firstly, the size of the generator. Secondly, the voltage of the generator. Thirdly, the type of transfer switch. Fourthly, the requirements of the NEC. Fifthly, the local codes and regulations. By carefully considering these factors, it's possible to design a grounding system that provides adequate protection against electrical shock and equipment damage. Grounding is not just about safety, it's also about ensuring the proper operation of electrical equipment. A properly grounded system can minimize electrical noise and improve the performance of sensitive electronic equipment. In addition to following the NEC requirements, it's also important to follow industry best practices for grounding and bonding. This includes using high-quality grounding connectors, ensuring that all grounding connections are clean and tight, and periodically inspecting the grounding system for corrosion or damage. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections can corrode over time, reducing their effectiveness. The grounding electrode should be checked periodically to ensure that it's still making good contact with the earth. The resistance of the grounding system should be measured periodically to ensure that it's within acceptable limits. A high resistance grounding system can indicate a problem with the grounding connections.